Well, good morning, everyone. Welcome to our ITS student research presentation. And my name is Siwei Hu. I'm the host of today's event. And we're very fortunate to have three speakers to speak with us. The first one is Benjamin, working with Professor Ricci, and the second is PhD candidate Guo Liang, and I will be the last speaker of today. Before we get started, we'll have Professor Ricci, Director of ITS, give us an opening remark and tell us more about the event. Professor Ricci.
All right.
Give a warm up for Professor Ricci.
Thank you, Siwei, and thank you, everyone. So I just want to give you a very brief welcome. This is a terrific event. We're very proud of our presenters this morning, giving presentations that I believe are going to be presented at the International Urban Freight Conference and also based on doctoral dissertation research. So as Siwei said, we've got three really intriguing presentations. We're very proud of our students, all of our students, and our three that are presenting this morning, especially. The International Urban Freight Conference is a very prestigious and important event. So for three of our students to be accepted with presentations is really a major accomplishment. So I would like to recognize the sponsors this morning. The flyer that Dr. de Guzman prepared outlines those. We have quite a few sponsors. Very, very pleased to acknowledge the support of the Port of Long Beach for this event, as well, of course, as our ITS Graduate Student Association, our PSR UTC, the UCITS Statewide Transportation Research Program, our RIMI initiative, and the NSF Smart and Connected Communities project that Professor Hyland leads. So three intriguing presentations, and really look forward to hearing each of these presentations. So thanks very much for joining us, everyone. It's going to be a very interesting morning, I believe.
Yeah, thank you, Professor Ricci. We'll talk about a little bit of housekeeping issues. So each presenters will have 20 minutes presentation followed by 10 minutes Q&A. And for those of you who would like to grab breakfast, we have some refreshments over there. And without further ado, we will get started. The first presenter will be Benjamin, and Professor Ricci will be introducing Benjamin.
Okay. So fortuitously, I met Benjamin when he was a first-year civil engineering advisee. I don't know if, Benjamin, that was random or if you chose me, but it turned out to be fortunate, especially for our research group, and I hope for you too. So Benjamin really impressed me immediately. He's a great student, strong motivation to specialize in transportation engineering. And he volunteered to contribute to a project, a CARB project that we had at the time on freight locomotive and rail car identification. This is part of California's transition to zero emission technologies. So this experience stimulated his interest in decarbonization of rail freight transportation, the potential for emissions reductions to benefit disadvantaged communities. And that's what we're going to hear in terms of some of his latest work in that area this morning.
All right, thank you, Professor Ricci, for your introduction. Let's give a round of applause for Benjamin. And thank you, Benjamin.
Thank you, Siwei and Professor Ricci, for the introduction. So this is a little bit of introduction. I'm Benjamin. I'm a second-year undergraduate doing civil engineering. So I've been working with Professor Ricci for about a year now. I believe I started like around March of last year. And where do I get my slides?
Over here. Yes, I think so.
Okay, here it is. Okay,
Sure. Would you like to share screen?
Oh, yes. I would.
You might want to use this.
Oh.
Yes.
Okay, so today I'm going to talk a little bit about the research that I've been working on for the past like 6-7 months, which is about measuring the impact specifically of rail emissions. Some of you who were here during the fall might remember that I covered a presentation on the same topic, but I have since fall and now I have updated a little bit of my methodology. So as obviously the world gets more aware about climate change and the effects of like transportation emission, we kind of work to reduce them, right? But when you think of like technologies, like cleaner technologies, for example, like they're usually in industries like automobiles or for like trucks. Rail comparatively has not had as much attention on it compared to these other industries, and as a result, it hasn't really implemented as much of these zero emissions technologies. Current methods, in order to actually figure out how to reduce emissions, one of the first steps is actually understand what impact they're actually causing. And to do that, we have to measure, have a way to actually measure what the impacts are, right? However, current methods usually aggregate this type of data by usually at the county or at the state level, right? And we don't really have a way to calculate emissions on for example, smaller areas. If you take San Bernardino County, for example, emissions are usually calculated yearly for this entire area. But if you're looking at rail emissions, for example, you know that it's probably just going to be concentrated around these lines. And this map where the green is, it actually shows where the disadvantaged communities are, which is something identified by California in 2021 in a Senate bill, which basically targeted certain communities that were being impacted by, among other things, emissions to target for climate investment, for example. And so one of the things that my research aimed to do was to be able to calculate emissions in smaller areas. So instead of doing it for the entire county, we wanted to figure out for a smaller area, over here or over here, in the areas that are most burdened by rail. In addition, there are current methodologies that can calculate emissions for at an individual train level per train. But the issue is usually these are only for intermodal cars, which basically what they do is they calculate the weight of the container. And that's a very systematic way to do it. But there's also another type of rail car, which is manifest rail cars, which haul a different variety of freight and the same formula basically can't be applied to them. For example, you have auto wraps, which have automobiles, or tank cars, which have oils and other liquids. And it's not as easy to calculate the weight of that as it is for counting the amount of containers, for example. And so basically what we want to do is we want to have a way to calculate the emissions for each individual train. So we can get a daily emissions level or a weekly emissions level in small areas. Okay, so the area of study that we chose was in Barstow. It's located in San Bernardino County in the Mojave Desert. And it's in addition to being a major rail hub, it's one of the stops along one of the major freight highways, which is, I believe, the Southern Transcom. So basically, a lot of trains will go from LA, from the ports where they pick up containers, all the way up to Chicago, and Barstow is one of the major stops for that. Another reason we kind of chose Barstow was because, as you can see with the map, it has a lot of disadvantaged communities around it, some of which could be heavily impacted by rail. And so actually what we have at Barstow is we have a sci-fi we have a camera set up there that can capture a sci-fi view. And here's an example of a little bit of what the data looks like. And so basically what our research team was able to do is basically you can get the footage of the trains passing by, right? And we have a model which uses YOLO to kind of identify in real time. And this was actually developed by our research team, which includes William, who will talk, in the next presentation, right? But anyways, the important thing is that this basically gives us the data on what locomotives there are and what rail cars are on those trains and exactly what type of rail car they are. And that's important because the key steps in calculating emissions are the key steps for calculating emissions are finding out the total railcar weight and the locomotive emission rate. So railcar weight intuitively, if a locomotive, which is the thing in the front, right? If a locomotive has to pull more weight, then it's going to need more power to do so, and it's going to create more emissions as a result. And locomotive emission rate is important because they vary depending on when the locomotive is built. So typically, newer locomotives will have will be restricted to more stricter emission standards, and they'll have like cleaner engines as a result, compared to like a locomotive that was built in like the 90s or 2000s.
Benjamin,
Yes.
what does YOLO mean here?
YOLO is like the model. Okay, let me pull this up. So YOLO is basically the model that is doing. Here, let me walk. It's doing the identification in real time. So this the actual model part wasn't too much of the research that I did. That was more like Guoliang and the rest of Professor Ritchie and Andre Tuck. But I was basically able to use
UCI model? Was it a UCI model?
What does it stand for?
you only look once.
Because we know
You only look once.
it is.
You only
Yeah.
look once.
But how is that related to trend? That's what.
You only see the rail car pass once and you classify it. I don't know, that's my guess.
That kind of vibe.
Representation model. That's the name of the graphical. That's the name of the graphical representation model. It's just called YOLO.
It's a generic one.
Got it.
Oh, it is.
Sorry, I thought it might be.
Yeah, it can be used for any other purposes.
Okay, it has nothing to do with transportation.
Yes, but in this case, our team was basically able to use it to identify these types of rail cars. So we would train the model basically to identify, oh, this is like a container with a horizontally stacked with two containers, basically.
Thank you.
So one of the issues is we need total railcar weight and locomotive emission rate, right? But if you notice from this footage, you're not able to tell how much this locomotive is emitting or like what the emission standards are, nor are you able to tell what the weights of the railcars are. So that's one uncertain point in our data. And previously we would use like average metrics for that. But that's one of the major changes that I've made from fall to now. So the idea to kind of get around that is to basically use like large data sets that have these metrics that we want, whether it's railcar weight or a locomotive emission rate. So one of the things when we first started, we wanted to get like a sample of daily emissions. So that's why we used 24 hours of data. In this data set, where there included 70 trains and around 6,500 railcars. The actual number is a little bit higher, but I will get to that in a later slide. Okay. So as I was mentioning, one of the problems with this model is that it's completely horizontal. So in the case that there are two trains that pass each other at the exact same time, which happens a decent amount because Barstow is a pretty big hub. So when you have two trains at the same time, basically the model is only able to the model can only identify the rail cars in the train that is closest. So if you notice the locomotive for the train in the back here, it's not being identified because it's being blocked by the rail car in the front, right? So for this, we would basically have incomplete data for this train. So we just ended up taking it out because we didn't have complete data for that. And so in our final results, the actual results that we have will be a slight underestimation of what the actual results are because we just took this out, basically. Because we had no way to actually identify some of the cars in the back.
So how about the weather condition, shadow, and would those impact your classification identification results?
So in terms of like weather, I think one of the biggest concerns that we had was the model sometimes wouldn't work at night, right? It wasn't able to identify the things at night. That was also something that Guoliang worked on a lot of the time, but he basically worked on developing a model. I believe we had basically two models, right? So one that could identify it during the day and one that was specifically trained to identify rail cars at night, basically.
Or foggy or heavy rain or.
Yeah. But I think in the data set that we had, we didn't run into that problem.
Okay.
Another thing about Barstow is that the background is like completely white.
Oh.
Some of the other sites that we're actually working on, for example, there's a site in Banning. There's like a giant mountain in the background.
Yeah.
And so we would have to work with background subtraction, which I believe is actually in Guoliang's presentation. But okay. Okay, so to reiterate, one of the two major things we needed was the railcar weight, and we can't get that from just the footage. So one of the data sets that we relied on was the rail waybill, which is basically a giant data set that has a sample of all like trains and rail cars that operate in the US in a given year. And it's compiled by the STB or Surface Transportation Board. And it has a lot of data and a lot of the metrics which we reuse. We're including like weight and railcar type. So when we filtered through the Wavebro data, what two of the main things that we used were railcar classification, so that we could get railcars that matched with these type our specific definitions of railcars, since it varied a little bit. And then the other metric we used was location. Because what we found was actually there was a pretty big difference between railcars on trains that were going like out of California versus like into California. Here's an example. This is like an open hopper. It holds like grains or like wood chips or like coal, that type of material. And what you'll notice here, basically this is like a CDF plot basically. And so what this is saying is this is like the distribution of all of the open hopper. So for example, you'll see that around like up to like 0.3, this line is constant. And that just basically means like 30% of the open hoppers that are going into California from wherever are usually traveling empty, since this is the weight of just the empty railcar. And then, for example, here you'll notice a giant line, which is up at like around 143, which is the max weight. So you notice a lot of the ones leaving California are actually traveling like completely full at the max weight. So this just basically shows that there are differences between railcars on trains that are going inbound versus outbound, and that's why filtering for location is important. Yes.
I'm wondering why there's so much in the middle of this distribution, and why it's not either completely empty or completely full a big chunk of the time.
Corn.
Yeah,
Corn,
sometimes
alfalfa.
that's a good point. Sometimes they'll
Oh, the weight of
they'll fill it up. Yeah, this is a weight metric.
Yeah, I gotcha. Okay.
Sometimes they'll fill it up, but the material inside may not be like that dense or heavy.
Or actually, I mean, no cars between 50 and 100 tons.
Right.
It's flat, right?
Mhm.
No trains.
Yeah, basically very little.
Or
Hopper.
either really light or really heavy.
Uh-huh.
That's how the trains organized. Or
Well, it
used.
depends. Each rail car has its own unique distribution, and that's another reason why we have to classify it by different types of rail cars as well. Yes.
We consider piezo meters on the truck side. So kind of as you can also use this as a wayside detection system.
Sorry, can you explain what the first thing was?
So piezo it's like a pressure sensor. So based on you can measure the weight of the rail car based on how much pressure it's applying to the rail.
I think one of the limitations is that we don't have access to like the physical track itself, so we aren't able to like install that. The closest we can get is like with a camera.
Got it. Okay.
So,
Yeah, I think the track's privately owned, right?
yeah, but BNSF. Yeah. Okay. So the second major component was emission rate, right? Well, how much are the locomotives emitting? And though actually the data set that we used was the BNSF locomotive fleet, which is basically it's like a California Air Resources Board document that compiles all of BNSF, which is one of the major operators for at Barstow. And it basically compiles all of their locomotives and what their emissions rate is. And that's what this table is kind of here. I took a sample of it. And so basically you'll see that basically what this is saying that is in their data set, there's around 3 locomotives that have an emission rate of like 1.1 and 266 that have like an emission rate of 1.2. Knowing what this emission rate and the unit means isn't too important for this, but yeah. So for EPA tiers, 4 represents like the newest tier. So these are like the lowest emissions. And 3, as you go down in the tiers, the locomotives get like older and more dirty. One of the things we did for this study was to filter out like short haul locomotives, which are locomotives that like operate like mostly in the ports and not for like long haul, right? You can tell it's a short haul locomotive because I filtered it out here, but sometimes you'll see like a number that's like 5.5, and then you'll see like a 14 or 15. And you know that locomotive likely isn't being used for long haul. If you remember, Barstow is like all the way over here. So a lot of the trucks that go through Barstow from the ports are usually going to be long haul.
So can you explain the unit of the emission? I know it's gram per bhp.
Okay, so okay. Actually, that unit is not complete. It's supposed to be, the full unit is supposed to be grams per brake horsepower hour.
What horsepower?
Brake horsepower.
Brake?
Yeah.
Oh.
I will be honest, I have not studied too much into what that unit meant. I just know how to convert it to grams per mile.
Fair enough.
Sometimes
Per
that's,
mile. Yeah, that's consistent with vehicle emission unit, right? Which generally is
Yeah,
gram
yeah.
per mile. Yeah, so this is not what I,
okay.
Yeah.
So now that we have like both of the data sets for and distributions for both railcar weights and locomotive emission rates, we use the Monte Carlo simulation to kind of assign railcar weights and locomotive emission rates from these data sets. And basically the idea is once we simulate this enough times with assigning railcar weight values, eventually the weight values, for example, we'll get a distribution that is close to what the actual distribution from the Waybill data set is. And so this is basically designed to just address the uncertainty with the fact that we don't know what the actual weights are. And this is the best estimated guess that we can get. So basically how it works is you have this CDF plot, right? I've explained a little bit of how it works. So basically what you do is you take a random number from 0 to 1, right? And then whatever the value that gets, for example, 0.6, you draw a horizontal line until you hit the graph. And then when you go down, that's the emission rate, for in this case, of whatever that locomotive you're doing is. So for example, here for a railcar weight, let's say we had one that was like double stack, which is basically the one with like 2 containers on it. So for example, if we pick the value of 0.6 here, we would get our railcar weight for this specific railcar to be around like 112, 113. And basically you repeat that for every single railcar in the data set, which we were able to get from, if you remember, from this step 1. And in for each train, right, we also know the amount of locomotives. And so you run this plot X amount of times for however many locomotives there are. And so once you have like estimated values for railcar weights and locomotive emission rates, you're basically able to determine emissions of a single train. And basically you run this simulation where you randomly pick a number and assign it a value multiple times. And so basically from the results that we got from this, we were from the 70 trains and around 6,500 rail cars. Remember, this is a slight underestimate. We got around roughly 3,000 tons of NOx and 100 tons of daily PM. It's a bit hard to contextualize what exactly these numbers mean. So we had a very crude estimate, a very crude conversion into amount of trucks, which is about 40K trucks worth of NOx and 90K trucks worth of PM. I will acknowledge that this is pretty crude because there are also a lot of factors that go into calculating the emissions of trucks, right? But what this goes to show, these numbers are pretty high. But what it goes to show is that trucks have been getting a lot cleaner compared to rail. That's why these numbers are so high. Because intuitively, if you think like a truck that's zero emissions, even if you had like a million zero emissions truck, it wouldn't produce like nearly as much PM as this, for example. And so basically, just to summarize, this methodology that we have is basically able to calculate emissions at an individual train level. And we being able to calculate emissions at a train level allows us basically to estimate like the impacts in like a specific area, like Barstow, for example, and see what the impacts, see what the emissions produced in that area are. Some of the future. Yes, Professor Hyden?
No, go ahead.
Okay. We save it for Q&A. Okay. Some of the future work we have is to actually put air sensors out there at Barstow and see whether those numbers actually match what we're calculating here. We actually have an air sensor deployed out at Long Beach right now just for testing. And the plan is in the future that we can bring it out to Barstow and see whether it matches up with our current methodology. Another goal that we have for this is to see whether to actually get more community impacts onto this. As you can recall, we have the emission numbers, but it's hard to tell what the actual impacts on the community are. And so that's something we're hoping to address in the future. Thank you, and I'd like to open it up to questions. Yes.
Yeah, I think it seems like then a lot of if you wanted to get more accurate, I know you don't have access to the right of way, which is some of the stuff I was suggesting before, but it seems like for the exact locomotive, I would suggest two changes, is that every single locomotive is printed with a number. And there's public databases maintained by often the public that tracks the exact type of and the history of that locomotive. This even like specific knows what happened to that locomotive, where it's been spotted, that's the engine, what kind of fuel it's using. And then the second part is that even if you cannot read the number, if it's too blurry, you can't look up that number in the database. There's only a few thousand trains. It's very easy to figure out what type of train it is. You can look at the radiator type, and then you can identify, is it a EMD, is it GEVO, and that will be more specific, because the main thing I'm seeing is the livery and the company, and that often has like very little to do with the actual emissions. So I would encourage like looking into the training a data set on if you can't read the number, look at the radiator and then look at the hoods of the train, and that will tell you it's the exact model of it. To address your first point, we have tried using the number to kind of identify like when the locomotive was built, but there are two issues with that. One is most of the ones that have like locomotives and when they were built were by like sites created by like rail fans, and they usually don't have data. Or they usually don't have data for each individual rail car. They'll like combine a bunch of numbers together and say that, oh, these are all built at the same time. The other issue is it doesn't work for emission rates, because you can tell you can tell what year the original locomotive was built, but if the locomotive was refurbished and set to a stricter emission tier, that's not listed. So basically, we can't tell what a locomotive emission, even if we have the number and the original year was built. We can't tell what the emission standard is because it could have been refurbished. Got it. Okay.
Yes.
Can you go back to the results slide, the distribution? Okay, so this is like 1 day of trains, right, in rail cars. And you end up boiling it down to this 90K trucks and 40K trucks, which I think is nice. I'm just wondering like what the value of the Monte Carlo simulation was in the first place. Like, why didn't we just use the means of each of the railcar types and sum them up?
Okay. Originally, we used means. And one of the problems with that, I was showing in the distribution, is that the mean will vary significantly based on the distribution, for example. For example, this is one of the things that we kind of addressed, but we didn't cover too much, was that sometimes railcar weights may be skewed. For example, if you have a train with like sometimes a lot of for example, okay, we're gonna take hoppers here. A lot of the hoppers that are empty may be traveling together on the same rail car, for example. Or a lot of the hoppers that are full are all traveling on like the same rail car. So there's that kind of correlation which makes it not independent, right? But that's something that Monte Carlo isn't completely able to address, because each rail car weight is taken like as an independent occurrence.
I mean, you can do multivariate Monte Carlo, but I think it's more complicated. It is more complicated.
Yeah.
I mean, I'm generally in favor of the method, but here I'm not sure what additional value it's providing for like this 1 day, right? Because what is the use case here? We want to communicate to policymakers, politicians, community members, how they're being negatively impacted by a lack of regulation from the rail industry, right?
Or rather, there is regulation, but it's happening at a much slower rate compared to other industries.
You want to tell them the damages or the harms that they're facing in the current situation. And the distribution is beneficial, I think, in some ways, but maybe not for 1 day, right? You'd want to know like over the course of a long period of time what the distribution is. So you have one day distribution that you're doing many times.
But technically, even with 1 day, you're already having like over like 6,000 different rail cars. So you're basically running the simulation 6,000 times, albeit with a bunch of different distributions.
Yeah.
But I feel like
it's not bad what you did. I'm just saying, could it have been a little bit more simple and parsimonious and not lost on
that's true. But I think if yeah, I agree with your point that if we wanted to expand this to maybe like weekly or monthly or something, we could that the Monte Carlo would actually probably fit better for that. Professor?
Yeah, so yeah, also for the results, I mean, first for clarification, do you consider 90K trucks to run the same mileage as
Yes.
70 trains?
Yeah, so how we calculated the distance factor in this was we calculated the distance that the train would run in Barstow, and we used the equivalent distance
Yeah.
for that.
Yeah. But then conceptually, we know, for trans trucks, they are used to transport freights, right? What matters is the maybe 1 million ton miles of freights, goods that we transport. So, there's a kind of overhead issue. Maybe 90K trucks. Did you guys consider, what is the freight? What is 1 million ton miles of freight they are able to, move versus 70 trains? Are they comparable?
When I first started doing equivalent like conversions to trucks, freight was kind of one of the things I considered, but the fact that for like manifest rail cars, right, which there are so many different types of them. There are only 4 here, but our total list has like 12 or 13. Basically, you have to have an equivalent amount of freight for every single one of them. And for like auto racks, for example, so basically like automobiles like go inside here.
Right.
You don't always know how many, whether this thing is like completely full or like possibly completely empty or like half full. So.
But I think that is actually very important, if not the most important thing that we should consider, like how much
equivalencies?
Yeah, goods, the freight they are able to carry. If they are comparable, then that makes sense. If, for example, the trains can carry significant more freights than these trucks, then then I would argue maybe the comparison may not be fair to trains or vice versa.
So basically what you're saying is even though trains seem like they have a lot more emissions,
Yeah,
if they're hauling like even more freight,
yeah,
maybe it might be worth it.
exactly. That is one comment. Another comment is that, I mean, emissions is important. This is also related, to the emission as well. But we know that the trucks, have caused damage to roads, while the trains, they're damage to the rails and things. I think that might be important to consider.
But I think that's a little bit more like abstract in terms of like trying to put a number to, what are the exact economic like value of the damage of trucks being on the road, for example.
Yeah, not even just economic, also environmental. When we try to repair the roads, that's caused a lot of environmental emission. But not this type of emission, but that is significant. So that's another comment.
Thank you.
Yeah, thank you.
Any other questions? If there's no questions, then we will welcome our second speaker, Guoliang Feng, PhD. The stage. We would like to invite Professor Ricci to introduce Guoliang. Right, Professor Ricci.
Yeah, I'm just trying to get there we go.
Thank you.
All right. All right, so it's my pleasure to introduce Guoliang Feng, who is a key member of my research group, and we expect a soon-to-be PhD graduate. Guoliang's cutting-edge research employing emerging sensor technologies and especially AI-powered processing methodologies has been pivotal, really, in advancing the state-of-the-art and addressing key data gaps in support of more sustainable freight transportation that involves both heavy-duty trucks and also rail freight. So his presentation this morning is going to describe some of his latest contributions in this area.
Thank you for the introduction, Professor Ricci, and welcome candidate Guoliang Feng. Maybe I help you share screen.
Hi everyone. I'm glad to share our research AI-powered with the framework for real-time locomotive and rail car monitoring in here. And so this is the overview of my presentation. It includes 6 parts: background, data collection, methodology, results, conclusion, and limitation and future works. Firstly, I will share some background why we do this, why this research is important. Because this plot is U.S. ton miles of freight in recent almost 20 years. You see, the rail is significant because rail almost take about 6% of modal shares, and rail in California is also important. Such as in California, it's in rail it's planning to have 300 growth from 2023 to 2015. Because Benjamin already saw what is the locomotive and what is rail cars. Here I just give a short videos to give you a sense about basic train components. For basic trains, it will be a locomotive and hold a lot of rail cars. So there are two data types in trains. Firstly, the locomotive. Secondly, the rail cars. This is the current data source for locomotive and rail cars. Currently, for locomotives, it is based on some. It is firstly based on North American locomotive reviews. It will give locomotive yearly statistic number, and secondly is a rail line annual counts. It will also give some annual counts for locomotives. And for rail cars, rail cars is relating to its commodity activities, such as this rail cars. It will hold some containers, and such as the tank cars. It will like hold liquids and some others. So rail car activity also important. But currently the rail car activity is based on static data, such as North American railways, where volunteers submit their weekly rail traffic reports to Association of American Railroads, and then BTS will aggregate their numbers to monthly counts. But even though that it will cover just about 90% of its units. So based on this, there are some limitations for its data source. Firstly, both of data are static data. They lack they are limited to spatial and temporal characteristics, and no real-time monitors. And other is each locomotive you see have tanks. It will help to track these locomotives, and actually the emission is also related to this database. So based on this, there are some limitations to researcher on rail surveillance. Based on literature reviews, there are just a few of researchers works related to rail surveillance. And both of their researchers, they are lack of night conditions. So most researchers are just like can surveillance in daytime, but for nighttime, currently there is no way to monitor locomotive and rail cars. Secondly, few researchers just like give some sample rail car locomotive. They just can surveillance for just for a few locomotive and rail cars, not that comprehensive. Thirdly, the environmental variability is important, because when trace works out, when the environmental such as changes, such as rain, such as the background changes, such as it is a cloud or clear background, but some ground there have some landscape, it will become more complex for rail car and locomotive monitoring. So based on their limitations, we purpose framework rail vision-based locomotive and rail car monitoring. We call it the rail WIM. So for our framework, it includes 5 modules. This is just an overview. I will go details over each module. So the 5 modules include the first one is the background subtraction, and second is the locomotive railcar identification. Third is the tracking, and the 4 is the tag extraction, and the 5 is the tag recognition.
So William, may I ask a question? I understand your study is video based, right? You earlier Benjamin also mentioned about nighttime, situation. So have you guys considered or anybody consider other sensors like an infrared light sensor, which could detect, trends, nighttime or LiDAR or any of those efforts? Are you aware of those efforts?
This is infrared camera.
Oh, it is.
Yeah, it is.
So by video, actually, you do have infrared.
Yeah.
Oh, so that's cool. That's fun.
So yeah, this I think this answers your questions. So we have here I just saw 2 data collection sites. Both of them are your gateway, your corridors in California. It is Boston and Benny. As you can see, the camera we use is the infrared camera. So it's a kind of it can automatically switch RGB and infrared. So it can capture the light and nighttime for both railcar and locomotive activities. And both of sensors are side view, so you can say they have a similar angle. Try to enhance the transferability. So and this is the data summary. You can just briefly review this. This is the data summary for each module development. Based on the data collection and our search on website, so we have definitions for different locomotives. So such as the US have a classification for based on locomotive railroad. BNSF, UP, NS, and Fuel Max and Amtrak and CKC. They both of them they are class 1 railroad in US. So this is important. So this is the definition for locomotive, and there are other definitions for rail cars. Yeah, I think Benjamin just also part of rail cars, but here is comprehensive for what is for the model can recognize the direct classes. So this is the definition for rail cars. And based on the collected data, I will start for the framework for this. Start to introduce framework for this methodology. So for methodology part, and you can see the background is variations, such as in first is the Boston. They are very clean and cloud background. So the model performs well in Boston, maybe not performs well in Benny, because you see Benny in some mountains landscapes. It will definitely impact the model performance. So we want to have a model. It kind of works well one side and also works well another side. So we investigate methodologies about the background modeling. Here we investigate the two methods. The first method is the conventional background modeling. Why we call it conventional? Because there are some pre-requirements for its modeling. The first one is because of our cameras have detection rules, so it can capture 3 seconds per buffer. What means per buffer? It will before the locomotive enter the detection rules, so it will record 3 seconds of background. So we can use this sample frame to compare with the other frames to extract the foreground. So the advantage is we get a sample frame and we compare with the background in pixel level. Then do some noise reduction and do some object enhancement and also do some edge detections and then mask the background. But this method has some limitation. Firstly, it needs to camera have a very 3 per buffer. And secondly, if the train is stacked, it doesn't move. So which means this will no background information. So the comparison might be failed. So we have another methodology. This is called depth-aware background modeling. Such as for this, each image in pixel level, it has a depth. So we use a model called depth average V2. It will calculate the pixel depth in these images. Then we can get a depth maps and get that distributions. And then here, then use Gaussian mix models to mask out the background. It will give, so during this situation, the methodology will give a cleaner foreground. So to enhance the model's robustity, such as here, I just compare the performance about conventional background modeling with the depth-aware background modeling. Here we define the foreground purity. It is the result compared with the true object errors with the foreground errors in the image. You can see the depth-aware will get a little higher in this box plot, which means it will get a little bit more cleaner foreground. So it will help us to next step for help us for the modeling part. So I give a visually look like for how this model look like, how this model works. So both of them are in binding, but you can see the depth the right hand is the depth aware, but the left is the conventional background. For conventional background modeling, some part it can not work well for some frame, but for depth aware, it can like keep its performance consistent. So after that part, we get a little bit cleaner foreground. So the second step is for module 2. Module 2 is the locomotive and rail car identifications. Here we use the you only look once, YOLO architectures. Why we use the YOLO architecture? Because YOLO can provide the optimal balance between speed and accuracy for real-time performance. And in this YOLO architecture, it is a bounding box based detections, which means it detects this reticular bounding box for each object use. And in this case, it is critical for its definition is the intersection over unions. It is IOU. So the definition is we have in training process, it have a bounding box. One bounding box is from prediction, one bounding box is from ground truth. So this definition, this is I plotted to give the definition of IOU, you can say. And okay, for this IOU, it is in range from 0 to 1. So more closer to 1, it is more better, because which means the predicted bounding box is close merged with the ground truth. So it is so for the YOLO, this is just a brief architecture. First is the YOLO use the backbone to features instruction, then it has a headnet to feature process and give a model final prediction. But I just saw some case in basic YOLO it not works well, such as this gondola, wheel car, and container on flat car to TU. YOLO, the original YOLO doesn't work well for the class. After analysis, the limitation is because YOLO treat height and width equally. They are equally weight. But in our case, actually it is not, because the width will be the width have some temporal characteristics. So well, okay, firstly, the model is developed based on frame. So such as some frames will capture the whole of their serial car, but some just capture half, but other just capture quarter. So the width cannot kind of like a stress cannot really reflect the your car or locomotive's characteristic. So I do simple analysis to say this is some body box because body box actually the body box information already can somehow help inform where this is what type of locomotive your class. So this is just the body box wide distribution for each class. So based on this, it shows a little bit a uniform distributor. So which means each class appear to capture enough frames to capture its visual characteristics over time. But in here for hint is which locomotive rail car hits. The hints doesn't change as time as it's passed by the detection rules. So this is the hit distribution for each class. Here you can see I use body box to give I use original body box to give some class. They are a little bit lower than the other class, such as the container flat car 2TU and the coil flat car Gold and world class. You see they are a little bit lower height than other class.
So Guliang, I suppose you have some ground truth data.
Yeah.
And also, the identified data. Are these based on ground truth data or your own identified data?
Yeah, this is based on ground truth.
Ground truth data.
Yeah, so the body box is very tight to locomotive and rail class, so it can reflect their width and height characteristic.
And how did you get the ground truth data? Is it available online or something?
No, Benjamin and our team want to.
Or you guys go to the real world to measure or something?
We for this ground truth, firstly we need firstly we collect the data in the videos, then we need to convert to images. Then based on images, there are some tools called label me. Then we can
manually.
Manually.
Okay.
Yeah, the ground truth need manually.
Thank you.
Okay, so based on this, we develop a real IOU. This is a real specific IOU. For the it will consist of 5 parts. The standard IOU, it will like a standard IOU as defined previously. And because in here the height is important characteristic, so we give a height alignment penalty, and also the center of this required the center of each bounding box also give a alignment penalty, and also expect the height between the height and the width ratio. So this is a two comparison between the IOU and the real IOUs. In the first and in the A and B, you can say the standard IOU they shows 0.7 around, but in this real IOU it will show just a little bit about 0.5. So it will give more height penalties. So which means in training data set, it will help the predict bounding box to better align with the quantum bounding box. Yeah. So and the C and D scenarios just so our use also not bad in when the bounding box is large. So this is some more results to help comparison the model performance in for IGB and inference mode based on basic Euro architecture and our IOU. Here I just saw the result. I just saw the results where the F1 score difference is more than 3%, and this is the last clone is the average R class. So which means overall average class we IOU a little bit higher than the basic Euro, but for some like a low profile class, it will significantly improve. Such as for black car, it can improve 6%, but and for and this below is some illustration for model performance comparisons, such as the first one. This is a base when it works on when the model is training on Bastos, how it performs in Bunny. You can see the model. This is a 2G, but the model cannot recognize it correct. And for second, it is a base YOLO performance. One is image one for this real class, it cannot detect and do classification, but based on our specific real YOLO, it can recognize and classification for this type of real class.
So I don't know the performance measure, but the baseline is already high, so high.
Yeah.
And you can improve 6% based on that. I think I would consider that significant.
Yeah. So this is
or even 4%, right?
Yeah.
Since the baseline is already 90 something, just like if you can improve your grades from 94 to 98%, that's a significant improvement to me.
Yeah.
All of them.
So this is because of until to module 2, what I presented was how it performs in image frames. But actually our data source is videos. So we need to associate different image frames, such as in this examples, you can see there are two image frames, frame N and frame N+1. But here you can see they are just the same objective, such as this is just objective 1 and objective 2. So we need to associate with them. And the associate based on the tracking. How is tracking? It is based on temporal characteristics and based on comparison of comparison based on the similarity of appearance and places. Here we just use the board sorting tracking to associate each frames. This is the existing algorithms we applied to this. The first one is when or downs. We need for this locomotives. You see there is some tag. We call it a tag. Actually, it is the locomotive IDs. With this ID, I guess it will help us to tracking for this because in each fleet it have a unique tracking ID for each locomotive, so it will help tracking the locomotives. And also not really the logo just so the brands, also some what is the type of this railroad. So this is the module 4 for tag and logo extraction. And for after this, you can see there are some I provide some examples for RGB and infrared tags. You see for some infrared black, some they are clear, but I also share some tags. They are not in good qualities, which means they are poor qualities. Even though human eye they cannot ground truth for this tags. So in the final, I will show the results because based on two metrics for this tag recognition. One is the correct tag recognition for tags. For tag, which means it is for all detected tags, but and another is the correct tag recognition rate for human labeled tags, which is over the tags we just when we can ground truth for the tags we cannot ground truth, which means we didn't consider in the second matrix. The third one is locomotive tag recognition. Even we extract the tag, but we need this convolution neural network to help the tag recognition. So which means this is the process for this how this CRN works for each tag. It also includes feature extraction and LSTM to provide the temporal information for its text. And in the final output, it will output the text and its confidence. So this is 5 modules for our framework. After these 5 modules, we will use uniform distributor for each frame. Then consider both of each frame's recognition and its confidence score to aggregate for its multi-frames result, get the result for each unique objects. 5 minutes. Okay. This is just some with partial relations for integration of modules. So you can see this is the left is the original videos and the right is results after module process. This is how modules works in Biny. I slow down the videos to give more better relations. You can see it will works both on daytime and nighttime. Okay, this is a framework validation at faster sites. So previously is the validation, but this is the summaries for each frame. It is summaries for framework this at faster site. Here you can see overall our framework can achieve more than 90% accuracy. And in this one you will see base YOLO with background and our real YOLO programs. You will see it will significantly improve for low profile real cars. And also the tag detection and recognition rate in RGB mode, it is around 97%. In infrared mode for tag in night, it performs also not bad for this one. Yeah. And this is the transferability test site. So you will see the model transferability is similar with some with Basel, so which is also not a bad performance for this result. And this is my conclusion. So we developed a model can do 24-hour and 7 days monitoring for locomotive and real car using infrared equipped cameras. And also we developed the depth aware subtraction to robust model performance. And also we proposed our real YOLO to improve the accuracy for low profile real cars. And both of each class in RGB and infrared model, it provide a high accuracy. So the limitation is and the first limitation is side field camera view. And it doesn't consider the occlusion situation in there. And the second is for some text that human can go on to it doesn't consider in it. We need maybe another sensor to improve tag readability. This is some limitation for its work. So that's all for my work.
Any questions, comments, and thoughts? Yes, sir.
Well, I thought it was actually very, very cool. I think even kind of one of the big problems is the U.S. rail networks. You cannot really know where the freight cars are. So I think even if this is a very good presentation on the visual processing in kind of these outdoor scenarios, I think another thing that you can do to increase, I know that the 5% is maybe if it's still a lot for you, you can just have multiple cameras from different angles. And there's often also there's some sites on many railroads which are lit, especially at the control points. That's where they're lit at night. So that's another place that you can kind of set up, or you can set up 2 cameras and kind of get a multi-view. And then if it passes, both checks, then you can say that definitively that it is that rail car passing. But this is very good. Actually the main application I can see is just like a visualization for like a freight railroad tracking, since there are those software that exists right now, but it's actually all human input, like people are inputting in. So this is, if this is to automate that system, it's be very impressive.
I ask
Yes, sir.
Oh, yeah, one more question. I mean, for, this, you've been using, the CNN and all this method. I'm wondering if you try or if the large language models, I don't know, whether that will be helpful at all, because I did use some of the very strong in OCR, especially if you guys tried it. My handwritten notes, I just, take a screenshot and ask you to, OCR my notes in the, cursive English, in the Chinese.
Yeah.
I'm wondering if you've been.
Actually, already it's a very good stress. Actually, I recently I done some for large language model, but it's not completely to share.
You are doing.
Because large language model, currently the most benefit for large language model I use it in the label free. So we didn't not go to data set. The just can use the with language models database to help to detections. Yeah, I did some test for images, for image frames. Now it's without I thought it's just 18.5%. So it might need some fine tuning. So I still investigate, but it's definitely a good stress. Yeah.
Okay, cool. Good to know. Thank you.
All right, thank you, Guo Liang. Let's give a round of applause. If you want to go to restroom, please feel free. But I will start. And okay.
Anyway, Professor Ritchie is going to introduce you.
Oh, Professor Ritchie. Professor Ritchie is. Hey, Professor Ritchie.
Yes, I'm here.
Thank you, thank you. I'm thinking of self-introduction, but thank you, Professor.
There seems to be a problem with my video starting. So, but if you can hear me, Siwei, right?
Yes, sir. Yes, sir.
Okay. So, all right. It's my pleasure to introduce our third speaker this morning, Siwei Hu. Siwei has had an extremely impressive tenure during his studies here in ITS. He's been a key student member and leader of our ITS community, and he's clearly another of our rising stars. This is actually exemplified by another honor that Siwei has recently received in being named Student of the Year by the UCI Engineering Student Council. So congratulations again to Siwei. Yeah, well, like you, I look forward to hearing more about Siwei's latest research in his presentation this morning.
Well, thank you, Professor Ritchie. Thank you. Don't mind, let me quickly share the screen. So let me, for those of you who are not familiar with me, let me give a brief introduction of myself. So my journey at UCI actually starts in the year of 2018. 2018, in the summer, I did a summer research at Northwestern University with Professor Mark Gunier. And afterwards, I kind of traveling in the United States and talking with professors. Would you like to have me as your PhD student? And then at the last stop, it's UC Irvine. And then that day, I met with Dr. J and Dr. Hyland, and then they talk about very interesting research. So I applied for UC Irvine. Finally, I get in, start my PhD journey and my American dream. And so Professor J and Professor Hyland started co-supervising me. And so whenever there's a beyond normal time to graduate, they will both Professor J and Professor G and Professor Hyland. And so they co-supervising me. And then the work with Professor J, we win the best poster in the IEEE conference. The work with Dr. Hyland, we won the first place in the TRB 3-minute thesis presentation. So my PhD work starts with Dr. J, the dynamic traffic assignment. I try to use peer-to-peer trading to guide the system to a better state. But however, the methodology that we use is optimization method. It does not provide a pathway to analyze the stability of the system, which means if you reach that state, can you stay there? So, and then my PhD work started trying to extend that from route choice to departure time choice. And Professor Jing is an expert in departure time choice and dynamical system modeling. The approach that Professor Jing used could help to study the stability of the system. So in my PhD work, mainly I use a different approach instead of optimization, approach rooted in control theory that provides a pathway to analyze the stability of the system. So, and actually today's work, today's presentation is my third chapter of my dissertation. So today's presentation will be managing travelers' departure time decisions at a hyper-congested network with marginal social cost pricing. The collaborators Professor Jin and Professor Jay. So let us give a little bit background of our study. So I'll start. So this is a policy background of study. Early this year, January 5th, 2025, New York City has become the sixth city still have the cordon congestion pricing. And this is the congestion zone of the New York City, joining Singapore, London, Stockholm, Milan, and Gothenburg to become the sixth city to have the cordon-based congestion pricing. What we mean by cordon-based is we just circle a zone or downtown congestion pricing. When the traffic enter the zone, you charge a fee. So the purpose of it is just to reduce congestion. And so this is the toll schedule of New York City. So from 5 a.m. to 9 p.m. on weekdays, they define it as a peak, charge $9. And in the off-peak, they charge $2.25. But as transportation engineers, we are interested in how can we properly set the congestion pricing by time of day to accurately reflect the impact of an additional traffic on other traffics. So, so how do we set congestion pricing in the static case? So X is the traffic used in the facility. It could be flow, or it could be a number of vehicles use the facility, and this is the average cost function, and the number of vehicles times the cost function is total cost function, and then we take the derivative with the number of vehicles. This is the marginal social cost, and this is the average cost, and then this is what we call marginal external cost. So in the static case, we charge a toll like Pigovian tax we set the Pigovian tax in the same amount of this. So this is how we set a marginal social cost pricing in the static case. But what about in the dynamic case? Dynamic case, the number of traffic in the using facility, you add a variable, time variable, and also the average cost at T, also add a time variable. So it becomes more complicated. So how to set congestion pricing in dynamic case, you first need to figure out the traffic dynamics. And you need to set pricing according to your dynamics. Sorry. And analogy is an analogy is this analogy. So this C of X incorporates the traffic dynamics in the static case. So in the dynamic case, you need to figure out that dynamic first. And then you need to set pricing, figure out the marginal effect of an additional traffic added into the network and its effect on other traffics. And then you also need to model how travelers respond to the pricing so that you see whether your congestion pricing works or does not work. And then you need to load it in your traffic dynamics again, and then to see how the traffic dynamic change after people changing their choices. So you might wonder, then what is the state of practice of congestion pricing settings? So this is Singapore. So Singapore has 2 congestion pricing zones. And then this is how within day, how the charge look like. Well, basically, they just target at 20 to 30 kilometers per hour on the arterial roads and 45 to 65 on expressways. And then if the 85 percentile speed is below like 45 on an expressway or 25 kilometers per hour on the downtown roads, they rise tolls. So what it tells us is it set in an ad hoc manner. So which means they don't have a mathematical model to do it. They just set some rules. When you meet these rules and you adjust the price a little bit, maybe $1, maybe $0.5. So as transportation researchers, we would like to know what is the proper way to set congestion pricing. What is the state of art? We talk about state of practice. A state of art is this paper by Vickery 2020. It's also this paper in my hand is torn apart, reading so many times. So talk a little bit about the history of this paper. So this paper is dated in 1991, so you see why there's a 2020 over here. It's actually Vickery passed away, but he didn't get a chance to publish this paper. So before 2020, only there were 3 citations. One by Arnold, one by True, one by Small and True. But Professor Jing requested a manuscript from Columbia University and co-edited it with Professor Richard Arnold and actually published it in the year of 2020. And in this paper, it has 4 sections. One section is model the congestion in downtown Manhattan, which is getting the traffic dynamics. As we show you in the previous slide, you need to get the traffic dynamic first. And then in this section, estimate marginal social cost based on the traffic dynamics. And this is section 3. And section 2 models how people adjust their departure time, how people adjust their departure time based on the price that they charge. So how people respond to the pricing. And then section 4, Vickery has a method to solve the Vickery's bathtub model from T to T plus delta T, capturing the curvature of the network fundamental diagram. So a little bit background. So researchers have been trying to extend this Vickery's paper, like Professor Jing, by relaxing Vickery's bathtub model, the negative exponential distribution. Professor Jing get the generalized bathtub model, and then by extending Vickery's dynamic from the bathtub model, and Professor Jing get a stable local dynamics. So which means extension of Vickery's work is very fruitful. Researchers have extended Vickery's work in many directions. However, no one has integrated all parts of Vickery's work with numerical data, with real-world data to see whether this whole thing works or not. So this is our contribution. So we are the first one to integrate 4 sections of Vickery 2020 with 48-hour New York City traffic entry data. So our contribution is not theoretical because Vickery did all the math, but our contribution is integrating everything and and testing this framework using the real-world data. So and if we put this framework into my dissertation, is actually the 3rd chapter of my dissertation. So my dissertation is managing travelers' departure time decision in the corridor level and in the network level. So what we presented is the 3rd part. So I will take a minute to thank my committee members. So I think I wouldn't able to do a dissertation like this in any other university except UCI. We have Professor Jing's theoretical foundation, day-to-day departure time models, and we also have Professor Jay's expertise on dynamic traffic assignment and Dr. Hyland's expertise in dynamic traffic assignment. And Professor Hyland's project funded our research. So I'm zero, they are hero. So I'm standing upon 3 giants in our field to establish this dissertation. So if in any other university, maybe if Professor Hyland funded my research, if I do some other things as dissertation, maybe other professor will not allow. But Professor Hyland is very nice. So always take a minute to thank the 3 professors that supervise me a lot. They are so in depth too. And then let's take a look at what this 3rd chapter is about. So as we mentioned, we want to properly set the congestion pricing for the corridor level And then and this requires a model to describe how the traffic dynamics and also how people adjust their departure time, and also how to set the pricing. So this is Vickrey's framework. So Vickrey's framework is like this: you have your demand input, the number of vehicles flow into the area, and then you have your supply input, total link miles, network speed density relationship, network fundamental diagram, and this is the Vickrey's bathtub model. What it is this is number of vehicles in the network by a time. So what this did is just simulates the number of vehicles by time of day. And then you do the marginal social cost calculation to calculate the marginal social cost at each entry at different time step. And then you calculate the price that you need to charge. Marginal social cost minus average cost equals to the price that you charge. And then you start to adjust your traffic entry rate, which is departure rate in the network level. And then you compare the net departure rate in the next day and your previous day. If there's not much changing, you say you treat it convergence. So it's basically just like this. And then we could talk a little bit more about the little bit detail, but just so Vickrey's bathtub model, it just describe how traffic propagates by time of day is what we call within day dynamics. And as we mentioned, after you get these traffic numbers, what you need to do is you calculate the marginal social cost based on this traffic pattern. So this a little bit too much, but what I try to say in these slides is traditionally, if you remember this function, this what we described in the very first beginning, traditionally in a static sense, what we try to calculate the marginal cost is what we call a steady state marginal social cost. What does that mean? So if in this day to day, this is axis day, this is axis t, so the cost function so only depends on the number of vehicles using the facility, is independent with day, independent with time t. So if this partial c, partial tau equal to 0, then it's stationary state. And if this equal to 0 plus this is steady state. So the steady state cost only related to the number of vehicles using the facility. However, we need to use dynamic. We need to consider the within day dynamics. So we need to introduce the day variable. So what that means is we cannot use this traditional framework to estimate marginal social cost. So this is what Vickrey proposed, the marginal social cost. If you just look at this little figure, what this means is Q is the number of vehicles at a certain time, and X is the extra traffic added into the network. So what marginal social cost is, for example, originally from T to T plus 1, your curve will look like this. But because of you adding an extra amount of traffic, your curve will be not steep. So this amount of area is the marginal effect that you inflict on other traffics on the network. So what Vickrey did is he just calculated this part as the marginal effect that has on others. So what this figure want to illustrate is that if you add an additional traffic, for example, in 2 a.m. in the morning, it does not affect the traffic condition that much. But if you add an additional traffic in the 6 a.m. or 7 p.m., it's very congested. Maybe you add a little bit traffic, it gets gridlock. So the marginal effect, it depends on the time, depends on when you enter the network and how congested that state is. So what these slides just to try to show is by different time, you have different marginal social costs. And so what this slide is to show that is you have your number of vehicles and then you estimate your marginal social cost, and then you also have your average cost, and then you could calculate your toll. basically it's just what it tells us.
So maybe a comment or question. I don't know if we could justify this. Definitely, he just consider the congestion cost, right?
Yeah.
But we know that whenever we consider departure time choice, the scheduling costs sometimes could be even more fundamental. Because we choose leave at different time or arrive at different time because fundamentally we have some we don't want to be too late or too early type of thing. I'm wondering he just considered the congestion part.
Yes.
But in certain view, actually in his view, maybe the congestion cost is kind of like a secondary or maybe not as fundamental as the scheduling cost. I'm wondering, did he justify this kind of calculation anywhere?
Yeah, thank you for the question. Yeah, and scheduling cost sometimes is more important than congestion cost. And if in the point two model, you're balancing your congestion cost with your scheduling cost. But for Vickrey, he did not consider the scheduling. The way I think why he does not is because if you imagine in a network like Manhattan, and you have so many people, and then you have all this kind of heterogeneity in desired arrival time, heterogeneity in sensitivity to congestion, sensitivity to scheduling costs. So what Vickrey did is forget about all these things. And then what Vickrey is just, for example, this is Vickrey's day-to-day dynamic. Vickrey just compare the cost difference between day J and day 0. Day 0 is without pricing. And then he just assumed that travelers make their travel decisions only based on the increment of the cost based on your current day and day 0 without pricing. And then which time slot give you the minimum cost increment, and then travelers will shift to that time slot. So by doing that, definitely you will leave away the consideration of those desired arrival time and then different sensitivity. Yeah, definitely you won't be able to capture that. This is one of the drawbacks. But on the other day is that you don't need to be burdened by those heterogeneity. That's what I would say.
Okay, good explanation. And definitely we have discussions on this topic. But my opinions have been kind of swinging, back and forth. Sometimes I feel he's reasonable. Sometimes I don't feel he's reasonable. But anyways, good information.
Thank you. And if you have any questions, feel free to interrupt. Yeah. So what we describe is within day dynamics, how traffic propagates, evolve within day. And what about day-to-day dynamics? Day-to-day dynamics is how people adjust their departure time from day tau to day tau plus delta tau based on the pricing that they add. People might start shifting their departure time. This is how it looks like. As the answer to Professor G is basically on the cost differential on the current day and day 0, and then travelers start to look at all the time step, which time step has the minimum cost increment. So they start to shift to that time step. So and then it's Vickrey's numerical method. We won't get into details, but I just want to show you. So this is Vickrey's beta model. I simulate with different method. This is what we call my method. But and this is Euler method. This is Vickrey's method. So different. If you look at the number of vehicles, they are similar, different numerical method, but they do have some differences. But what's Vickrey's method? Why Vickrey's method is good? Because Vickrey's numerical method consider the curvature of the network fundamental diagram. If compares with Euler's method, the assumption is that from t to t plus delta t, this thing is constant times this delta t. But in vicrease, this thing could change. So it's just a basic idea without getting to the details. So you might wonder, what does it look like if we're integrating everything? This is our input data. We have the 24 hours demand data, but we multiply it from 24 to 48 because vicrease framework needs to start to estimate marginal cost from 3 a.m. And then we set the average trip length to 5 miles, total link miles to 225 miles. And this is the network fundamental diagram that we use. Free flow speed 30 miles and the jam density 200 vehicles per lane mile. Yeah, and the screen shows fundamental diagram. And this is the convergence criteria that we use. Is RMSPE. So what this means is it actually converges the pattern. But this is we can only call it practically stable because to be able to mathematically prove the stability, you need to find a Lyapunov function and to actually show that. But we currently are not able to do that at this moment because bathtub model is intractable. You don't have the analytical form like for the marginal social cost estimation, all those kind of things. So, but it's practically stable. And then, so this is our result from day to day. First, travelers shift their departure time from peak to off-peak. And another interesting thing is that when people start to shifting their departure time, the marginal social cost decrease very, very quickly. And compared to the last day to the first day, the maximum marginal social cost decreased by 94% from 9.63 hours to 0.51 hours equivalent. So by this marginal social cost pricing with departure time shifting, the marginal social cost decreased very fast. And since the tolling schedule is related to the marginal social cost, so tolling schedule also decreases pretty fast. And then the maximum average travel cost decreased by 40% with this departure time shifting and marginal social cost pricing. And this is the first day and the last day comparison. So what we see is the maximum value of vehicles in the network decreased by 46% when people start shifting their departure time. And then the minimum speed increased by 89.3%. So what that means is it actually worked. But as you see here, there's a little bit oscillation. We still need to dig into that to see what's happening out there. And then a little bit conclusion of our work. The main takeaway of our work is vicrease framework actually works. And after applying the dynamical marginal social cost pricing and day-to-day deferral and advancing mechanism, system converged to practically stable optimal equilibrium. Marginal social costs decrease very quickly from day to day. The maximum number of vehicles in the network decreases, which is the severity of the congestion decreases, and average speed in the network increases. And this numerical result also provide a practical reference for determining the magnitude of cordon congestion pricing. For example, if the 0.2 hour equivalent, if you have assuming you have $9 per hour value of time or even higher, then it could transfer this hour equivalent to the toll. So so this is the end of my presentation. Happy to take any questions and thoughts. Yes.
Great presentation. What makes you stop at 2,000 days instead of just resulting in like a flat traffic distribution over time? So like that is the last day, right?
Yeah.
The orange line.
Yeah.
So you just stop there. What makes you stop at and you name this is the last day, but you can just keep going on and then make it like a flat distribution, uniform distribution over time?
Yeah, I think we have stopping criteria. If this is less than a threshold, I think we set a 0.001, and then which means the departure rate do not change that much from day to day, and then we consider it converges.
Great. So my following question is that maybe it could be a suggestion. So instead of just you keep the simulation to the last day, you can like considering Professor Jin's suggestion, you can consider scheduling toast as well. So you can make some middle of those scheduling and optimizing. So you can stop at like not changing too much about the current departure time, but you can still make a very efficient traffic, like changing within 30 minutes only, not changing like 2 hours or 4 hours. So that would be, I think, more realistic in the future. That's my opinion.
I think it's a great suggestion to incorporate a scheduling cost. But I kind of need to think about it or need to think through it in a similar scenario, or more simple scenario, like a bottleneck model, point Q model. If I study through that, maybe I could be confident in how to extend this. Yeah, thank you, Yongkwan. Great. Yeah, Benjamin.
Can you go back to the slide with the word track?
This one?
Yes. So what time did you say the thing started at again? Or like what is time equal 0?
Time equal to 0 is like a 24 a.m.
Oh, so like at midnight.
Midnight.
Oh,
It's like,
so like if you're driving at like midnight, right? Can you explain why like after like 2000 days the speed will decrease that much? Because like I feel like if you're driving at midnight, you're like going to do that like no matter what. Like for example, if you're driving at work and if you're driving to work and you're like demotivated by the tolls to not drive at work, it's not going to move until like 12 a.m. right? So can you explain why like the decrease for speed or like the increase in vehicles would increase so much at that time? Or like I guess did you take that into consideration?
Oh, thank you. Thank you for the point that you bring up. Is the departure time shifting? Do you have a bound on that? Maybe you shift only to like 5 a.m. You won't shift even further to the 12 and the midnight or 3 a.m. Yeah, that we have not considered, but thank you for mentioning that. It's a really important. And then if to answer your question, why why speed decrease, why number of vehicle increase, it just we shift their departure time. They shift. If you don't mind. Yeah, so this is maybe it's not that clear, but it's increasing. The off peak is increasing. So that makes the that makes the speed decrease. But I totally get your point. Do we have to set a bound on the people to adjust the departure time? Maybe they only adjust to 5 a.m. or even 4 a.m. but not to the 12 midnight.
Yeah, definitely that is one, but I suspect it might have been related to the fundamental diagram. We know that with the green shields fundamental diagram, even at a low density, relatively low density, it still drops speed. But in reality, when this, it's a triangular or trapezoidal, with relatively low, the speed will still be at maximum level. I suspect it has something could be related to that.
They work fundamental diagram.
Yeah, if you're looking at the volumes on the top, right, it would suggest that it's maybe unrealistically sensitive to increases in number of vehicles, right?
Yeah.
If you're going from 0 to 1,000 in all of Manhattan, it's probably not going to actually have any impact on speed.
Yeah,
whereas your model
assuming triangular kind of level, but Sway and Vickery, That is another thing I might not agree with him using the ratios.
Yeah. I guess Vickrey screen shoes might be mathematically intriguing in estimate the marginal social cost because it's just linear.
Yeah.
Yeah, if you need to estimate the marginal social cost and in a triangular fundamental diagram or trapezoidal, that shape is not linear. It might be harder.
Differential.
Yeah, Professor Highland.
Oh yeah, just a question about, have you thought about considering like trip cancellation or mode choice, right? So in Manhattan, if you look at the congestion pricing data recently, there are just less vehicles in the network, right? It's not just that the people shifted their departure times. There are just fewer people that are going into the downtown area.
Yeah.
I missed this in the beginning.
Thank you, Professor Highland, for mentioning that. Actually, in Vickrey's framework, is modeling a response to pricing. Vickrey has 4 response: advancing, deferring, and suppressing and generation. So suppress and generation related to elastic demand. So we currently just consider fixed demand, but we should consider elastic demand. Probably is more insightful to see how people change, like totally cancel the trip, suppress the trip altogether. Any questions, thoughts, comments?
Maybe I have one. I mean, get to the results. You talk about small oscillations. I'm wondering, is that related to? I forgot. Did you update the toll every 30 minutes or every hour?
The
Vickrey's paper is every hour, right?
Every hour update.
It is every hour. So you have a constant fixed toll every hour.
Yeah.
But theoretically, it should be changing with time as well, right? So I feel that might be related to the, you can see, this kind of period there is that, small oscillation is kind of changing every 1 hour. You see what I mean?
Yeah. There might also because of the departure rate, because the departure rate has oscillation. So
Right, but yeah, my point is that because we are fixing the tolls every hour, I suspect that might be the reason that could lead to this local oscillations.
So the toll should be continuously.
Yeah, if it's continuously changing.
Thanks, Siwei. Great presentation.
Thank you.
So maybe you can check whether it's 1 hour, changing every 1 hour.
Yes, sir.
Thank you.
Yeah, questions, thoughts? Yeah, Kotaro?
Why did you take that long to reach the convergence? So it takes 6 years to reach the orange line.
Oh, yeah, if you count
Yeah.
6 years.
Does that mean it takes 6 years to reach that stable?
That's a really good observation.
So
What's the point?
that's so long to respond to the pricing.
I think very good question. This
How do you interpret the length of the convergence?
It's actually related to this BABD. It's how people sensitive to shift later, how people sensitive to shift earlier. What we currently do is we guesstimate, we guess a number for this,
Okay, got it.
but actually we need to calibrate it with the real world data and to set this properly. And another thing is this delta tau is what we say is equals to 1. So what you see is from day to day, but maybe this tau could be differently.
I mean, delta tau.
Delta tau.
So that should be really interpreted as iterations. Maybe not to show it as days. That's a really good point. Because that iteration times delta tau would really be the number of days.
Yeah.
What is the delta tau? That is a very good question because we never, because in my other simulations, I never explained, never thought about what should be delta tau.
Did you play with other values, BI plus 1 tau? So this is a this is a parameter for this model.
Yeah,
Affects the length of the convergence. Like
yeah. What
maybe
we
6 years is too long. And it's kind of unrealistic.
Yeah. So do you remember in my first study, I do have a delta tau and then the number of days iteration. I remember it
40 days.
40 days.
Yeah,
That is more reasonable.
That makes sense.
But yeah, that is true. In the second,
Also, it is just that patient. So wait for the.
40 days, okay, huh?
Yeah.
But but in terms of iteration, it's also really high. You see what I mean? Because delta tau is really small. But this here, there's no explicit definition of delta tau in Vickrey system. If we think about it.
Yeah, there's no.
Yeah.
Just iteration, maybe just presented as iteration. Not, I mean, that would be too long for that many years.
Yeah, it's an iterative approach to solve a optimal equilibrium.
Yeah.
It's more like my comment.
Yeah.
That's it.
Thank you. And I also
check my paper. Hopefully, I did not use this in my paper.
you use day steps.
Oh, day steps. Okay, so that's a little bit better.
Thank you, Seaway.
Yes, thank you. Yeah.
And in June, have a question from online.
This is day step. Okay, so that's good.
June said, is the pricing fixed or dynamic? If it changes throughout the day-to-day, how might that affect the stability of the departure rate? Pricing, dynamic, first answer June's question. And if it changes throughout day-to-day, if the price change out throughout the day-to-day, how might it affect the stability or convergence? The thing is, pricing, this is pricing, this is total pricing. See, it changed from day to day, yes, but it kind of decreased very quickly and then stabilizes. And then when your departure pattern kind of stabilizes, your schedule also stabilizes. Yeah. Any questions and thoughts? No, this might take too long. But any questions from the audience or online? Yeah, if not, we might just there's a chat. Oh, June said thank you. Yeah, thank you. We could discuss next time. And then another so today will be it will be the end of today's event. And another event is a week from now, April 11. We're fortunate to invite Lanzhou. Lanzhou is the director of Caltrans State 12 district, which oversees Orange County, oversees 1,000 employers and 3.2 million residents. So we're grateful that Vicky invited Lanzhou to speak with us. It's also associated with the SoCal CE Symposium event. So if you have time, please come join us 12:30 p.m. Friday to
12 o'clock is lunch, by the way, and 12:30 is the presentation. I'm not sure why it's like that.
Yeah, why 12:30?
So 12 p.m.
We're
lunch.
turning back time.
Yeah, so we hope to see you there. And with that, we conclude today's event. Thanks for attending. Thanks for your support.
I might be updating.
Yeah.
I did use day steps. It's a little bit better, but still very confusing.